Hi, everyone. This video is going to be replacing our normal lecture 7. So the Friday lecture that is not meeting in person, this is the video that we are doing instead. So we are going to continue on with our acid-base discussion. Then we will move into our organic chemistry language. The nomenclature and the functional groups are going to be a separate recording. And then we will move into the Newman projections to kind of finish out this video. All right, so let's get started. So we had talked about our acids and bases and the different categories. So hopefully you can go through and do the next 3 practice problems. So I recommend pausing the video, work through these, make sure you can identify which one is the stronger base. All right, let's go through it. The stronger base is going to be the amine. When we go through our factors, they're both neutral, so charge doesn't impact us. Then we look at our atom. We are comparing nitrogen versus oxygen because those are the atoms that have lone pairs of electrons. So that's going to be the most basic site on these molecules. So when comparing nitrogen versus oxygen, for the base, I want the less electronegative atom now. For acid, it was most electronegative. So base is just the opposite conclusion. So now I want the least electronegative atom, or I should say less electronegative atom. For the next one, it is our amide, and that is because we are comparing anion versus neutral, negative charge. It's going to be the stronger base. This last one, it is the structure on the right. It is the amine as opposed to the amide. The amine is going to be the one without resonance. So we are comparing the charge. They are both neutral. We then compare our atoms. So on our amide, we actually have 2 options. It could either be the oxygen or the nitrogen. The nitrogen is the one that is less electronegative. So I'm actually comparing nitrogen versus nitrogen. So you always want to watch out that you have multiple basic sites on a structure, or could have multiple basic sites. So for this molecule, we pick nitrogen because it's the least electronegative with a lone pair. So that makes that nitrogen the basic site. So we have nitrogen versus nitrogen. So that is still the same atom. And then we move down towards resonance. Our amide is going to have resonance because I have a lone pair of electrons next to a double bond. So I will get a resonance structure. Whereas the amine, there's no resonance. And we want the one with no resonance for the base. More resonance, stronger acid, no resonance, stronger base. All right, that concludes our acid-base discussion. So let's move on to the language of an organic chemist and our reaction vocab. All right, so looking at a chemical reaction, we need to know what assumptions are being made when we have it set up a certain way. So our reagents that are at the beginning of this arrow, so at the tail of the arrow, these are going to be our reactants, which I will frequently call starting materials, which I abbreviate SM. The reason that I call them starting materials instead of just reactants is because we also have reagents, and those 2 words sound really similar. So our reagents are typically written above the arrow, whereas our reactants are typically written in front of the arrow. Your reactants are usually what contain the greatest amount of your carbon scaffold, so the greatest number of carbon atoms. Your reagent is usually what's adding any other element. So it's adding hydrogen or oxygen or nitrogen, or it's acting as a base, or whatever the other role is, that's our reagent. So the thing with the greatest number of carbon atoms, that's our reactant. Everything else kind of goes as a reagent. They're all considered starting materials. And there's a lot of like leeway and ambiguity between this distinction. So reactants can be called reagents and reagents could be called reactants, like there's overlap. So this is not a firm separation, but just a general guideline that we usually call whatever's to the left of the arrow. Typically, we call them reactants. Whatever's above the arrow, we will typically call reagents. Then our conditions will be written below the arrow. Our reaction conditions are going to be anything like solvent or pressure or temperature. These are reaction conditions. It's anything to actually make it real. See, with our double dagger, this is our transition state. Which is sometimes abbreviated TS. This is where you have partial bonds being made and partial bonds being broken. So you have dotted lines, and it is not isolable. You cannot get a transition state in a bottle. It's not possible. However, our intermediate D can be bottled. So an intermediate is isolable, and it is going to be the product of a step. So an intermediate just isn't your final product. It is a product, but it's not the final product. It's not the end of a multi-step series. So if you have a multi-step reaction, so it's like step 1, step 2, step 3, intermediate will be the end of step 1 and step 2. And then your final product is what will be the end of step 3. That's what you're actually done. That's what you want. So these are what we're going to finally call our products, are E and F here. I should also note the brackets for the intermediates are not necessary. Sometimes they're included, sometimes they aren't. It's not necessary. When we look at a reaction coordinate diagram, A and B would go all the way to the left. C, that transition state, is what's at the top of the hill. And then here for this diagram, D is what's at the bottom of the hill. So this is the product of this step. Every step in a reaction will have one transition state. So in order to get to E and F, there's got to be another hump, another hill to climb, and then E and F are down here, and there's another transition state. So the intermediate is the product of this step. The difference between our starting materials, our reactants, and our transition state, that is the energy of activation barrier. That is how easy or hard it is for the reaction to go. The lower the energy of activation barrier, the faster the reaction. The higher it is, the slower the reaction. Delta H, the enthalpy of the reaction, is the difference between our reactants and our products. If delta H is negative, as it is here, then it's going to be exothermic or exergonic. So thermic just means heat. Gonic is referring to Gibbs free energy. So this is looking at the fact that the product is lower in energy than the starting material. That's what's giving us the negative delta H. If the products were higher in energy than the starting material, then it would be endothermic or endergonic. If it's exothermic, that is going to be typically favored. That's usually a spontaneous reaction that is favorable. Not every reaction that we do will be exothermic, but most of them will. Some steps we will indicate are endothermic in our reactions. We will have some steps that specifically are. For example, forming a carbocation. Anytime you make a carbocation, that's going to be endothermic. Some important key terms: kinetic control is talking about the speed or the reaction rate. Thermodynamic control is talking about the overall stability of the product or the relative energy. So it's saying that you are lowering the energy of your molecule or you are increasing the stability, specifically of the product. Gibbs free energy, that's our delta G. If we have a negative delta G, so that is less than 0, that is what makes a spontaneous reaction. Delta H, that is our enthalpy. That's the heat. T is the temperature. Delta S is our entropy. That is disorder. So a big thing in Gen Chem 1 was talking about enthalpy, calculating enthalpy. That's where you had like the coffee cup calorimeter, all that stuff was enthalpy, the heat of the reaction. In Gen Chem 2, that's when you were introduced to entropy, this concept of disorder, and then how to use the Gibbs free energy equation. How we care about this is we care with respect to bond strength and energy dispersal. That's what we're going to care about with our reactions, is just looking at, is it going to be a strong bond? Is it favorable to break, or is it not? That's how we're going to use this equation. And to be honest, we're not going to use the actual equation. That's how we'll use the concept. Equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. So there's no change in the concentration, but it's important to note that the reaction is still occurring. So the reaction is still going forward and back, forward and back. It's just the net concentration isn't changing. So if you have A going to B, your equilibrium constant, so you have the KF, for the forward is going to be equal to, or the K expression, KF is going to be equal to KR. It's just saying that they go back and forth. That's equilibrium. The last key aspect that we need to talk about is going to be our arrows. So our arrows are going to be a part of our vocabulary. It is going to be like a part of our alphabet. So our forward arrow is the single-headed arrow. This is the one that points to the product. Our equilibrium arrow can be either where you have the forward arrow shown in both directions on top of each other, or you can get rid of this little middle piece and show just the outside squished together. These are exactly the same. And all of the equilibrium reactions are reversible. I will typically use this one unless I forgot to indicate that it was an equilibrium reaction. So I drew a forward arrow and then I'm like, oh, I forgot, it's an equilibrium. These two are totally interchangeable. If we're looking at the equilibrium that favors the products, assuming that our reactants are on the left and our products are on the right, it's going to be a long top arrow and a short bottom arrow pointing to the favored products. If it favors the reactants, then we're going to have a short top arrow and a long bottom arrow coming back. Resonance is our double-headed arrow. It's where you have the two heads on either side. That is showing that movement of electrons through unhybridized p orbitals. It is showing that each structure doesn't exist in reality. The reality is the average of all those structures. Our curved arrow will show the movement of electrons, specifically the movement of 2 electrons if it has a full arrowhead. Our half curved arrow has a half head, and this is the movement of 1 electron, which will be radicals. We are not going to deal with radicals until the very end of the semester. So we're not going to be using this arrow until the very end. This is the one that we're going to be using the most of, is where we're showing 2 electrons coming through. Our retrosynthesis arrow is going to be this open arrow. So it's like an equal sign that was turned into an arrow. It is always going to point towards the synthons. Synthons are just proposed starting materials. Our dipole arrow is our arrow that has the little plus sign on the end, and it always points towards the more electronegative atom. You must use the correct arrow. You will lose points if you use the wrong arrow. You must use the correct arrow. This is our alphabet. So it's just the same thing as if I had written that word. That is the word dad. That is not the same thing as had, which is not the same thing as bad, which is not the same thing as pap. All of these words are different. They look very similar, just like our arrows. Our arrows look very similar, but just by changing how we draw this, where that straight line goes in respect to that hump, that is going to give us a totally different meaning. The same thing happens with your arrows. You got to write the right word. You got to write the right arrow. All right. Let's next roll into our alkane stuff and conformational analysis. So if you want to, you could pause the recording because I was imagining that we would have finished that in today's lecture, but the cockroach issue kind of slowed us down a little bit. So if you want to pause the recording now, watch the nomenclature and functional group discussion and then come back to this. That might help a little bit. I mean, not a whole lot. You can keep watching, but I kind of intended it to be in that order, but alas, here we are. So I'm going to go ahead and start the alkane section now. So our alkanes are going to be saturated hydrocarbons. So hydrocarbons only contain hydrogen and carbon. So that's why it's a hydrocarbon. Saturated meaning it has the maximum number of hydrogens possible. So if you think about a saturated sponge, that sponge is dripping wet. It cannot take another drop of water. It has all the water it can hold. Our saturated hydrocarbons has all the hydrogens it can hold. There are no pi bonds. There are no unhybridized p orbitals. There are only sp3 hybridized carbons. They are generally considered unreactive because of the fact that there are no functional groups, there are no pi bonds, but they are going to be good nonpolar solvents because they're generally unreactive. We're going to have a couple of types of our alkanes. Our straight chain alkane is going to be where they're all just straight across. We get this zigzag aspect, but they're just laying on top of each other. They stack nicely. We get this really strong intermolecular force, remembering that our intermolecular forces are the London dispersion forces, dipole-dipole interactions, hydrogen bonding, ion-dipole, and then ion-ion. Sorry, I had a brain fart for a moment. So here, this is our London dispersion forces. This is the non-polar interactions. So the higher the surface area, the increased surface area, is going to increase our boiling point and our melting point because we have increased intermolecular forces. Our branched are going to have a lower boiling point because they're going to have less London dispersion forces because of that decreased surface area. So the branched is just where you have something coming off. So if I were to try to highlight this, I can't highlight every single carbon without picking up my pen. So whereas the straight chain, I could highlight every carbon without picking up my pen. So branched is you have something coming off of that straight chain. These are examples of saturated alkanes. I know that feels redundant because I just told you alkanes are unsaturated or are saturated, but we have one example of an unsaturated alkane, which is our cycloalkanes. Which are kind of an exception. So they're a special consideration where it's still just a hydrocarbon. It's still all single bonds, but we lost two hydrogens to make the ring. So our molecular formula for our alkanes is a CnH2n plus 2. So the fact that I have 5 carbons here means that I'm also going to have 12 hydrogens. And I can know right away by using this formula that by plugging in 2 times 5 is 10 plus 2 is 12, that I know I have 12 hydrogens. I could also count that's 3 plus 2 plus 2 plus 2 plus 3. That gives me 12. Here, this is also C5H12. Whereas if I try to put 5 carbons into a ring, now it is C5H10. So my general formula for one ring is CnH2n because I lost 2 hydrogens. We're going to find that every unsaturation is going to result in the loss. So one unsaturation equals minus 2 hydrogens. You lose 2 hydrogen for each unsaturation. And our types of unsaturations are going to be pi bonds and rings. So each pi bond will be one unsaturation, and each ring will be one unsaturation. These two, the straight chain and the branch, these are constitutional isomers. Sometimes they're called skeletal isomers. Skeletal. I can't spell that. Skeletal or structural. All these words mean the same thing. It just means that they have different connectivity, but the same molecular formula. Your cycloalkane, this is not a constitutional isomer. It's not a skeletal isomer. These are not isomers. These are just different molecules. Because they have different molecular formulas. We'll talk about unsaturations more when we get to alkenes and alkynes. We'll talk about our isomers more when we get to stereoisomers later on in, I think it's chapter 5, later on. So conformational analysis. This is how we look at the relative energy of our molecules, how they exist in 3 dimensions. So we're going to look at the relative energy of rotational isomers, sometimes called rotamers, about a sigma bond, which are also sometimes called conformers. So our conformational isomers, rotamers or conformers are all kind of synonyms. They're all meaning the same thing. We're going to start out by looking at analyzing our Newman projections, and that's where we will end with these lecture notes. And then next lecture, next week, we will get into chapter 4, where we're going to look at our rings and our cycloalkanes. So starting out, let's look at our Newman projections. Ethane, from the nomenclature video, you're going to find out that eth means 2 carbons. Ane means with all single bonds. It's going to be our parent functional group. Means that it's an alkane. That's where the ane is coming from. It's an alkane. All single bonds. So ethane is where you get the CH3, where the carbons are bonded together. We can represent ethane in 2 forms, staggered and eclipsed. We can then also represent those staggered and eclipsed forms in 3 ways. We have our normal dash wedge, which is our normal line diagrams. Then we also have sawhorse, which sawhorse we're pretty much never going to use. Sawhorse is really only used, well, it's used in advanced organic chemistry classes for specific reactions, looking at trying to calculate bond angles. But we're going to focus on the Newman and our normal line diagrams. That's where we're going to operate. You can go through the sawhorse to get to the Newman, but to be honest, it's not necessary. And so what we're doing is we are trying to look down this bond, this staggered bond. So staggered is looking at the in-plane lines are on opposite sides. So the actual lines are on opposite sides. This is that zigzag, this is low energy conformation. The wedges are coming out at us, the dashes are going away from us. And whether you put the wedge or the dash on either side, on either left or the right side, doesn't matter, because really they're actually on top of each other. It's just that I can't draw it on top of each other and still have it be clear. So we show them slightly offset in order to make it easier to see. So whether you put the wedge or the dash on the left or the right side, doesn't matter. That's still equal as long as they're still pointing up from that top part. So what we're trying to do is trying to think what the best way to do this is. Wish I had a document camera. I'm going to pause the recording. Hang on. Okay, so that didn't work, but I will hold up the diagram here and then I'll switch back to the record or to the shared notes. So what we're doing is this is our molecule. So it helps if you can actually build the structure. So this is where having your model kit is really useful. So we have our 2 carbons that are in the middle, and then pretend that all of these are hydrogens on the ends. And so what we're trying to do is if we are staggered, so I have one going up, it's coming down. These are in plane and coming straight down. These 2 are pointing out at you. So this purple little one and the big blue one are pointing towards you. Those would be the wedges. And then on the back side, I have this green little one and the orange little one. On the back side, these are the dashes. They're going away from us. So that's what I mean by it doesn't really matter which one you show on the top, because you could either draw it like that or like that, and they're still in the same place. Whether this is, which one is left or right, it's just you've shifted it slightly that way or slightly that way. So it doesn't actually matter which one you do in the on left or right, as long as they're still connected the same. And the one that's pointing towards you is the wedge. The one that's pointing away from you is the dash. So what we're going to do in order to get into our Newman projection is we are going to actually imagine that I am positioned on the end. So I'm now looking down this molecule, straight down this bond, down this carbon-carbon bond. Oops, down the carbon-carbon bond. So what I'm doing is, so if this is my structure, I'm imagining that I am rotating it. And so then I'm going to be looking down this carbon-carbon bond. It is really hard to see this bond. As you can see, the back carbon is now hidden. It looks like I have 6 bonds to carbon, but I don't. There's another carbon back here. That's where our Newman projections are going to come in handy, is we're going to use a dot and a circle. A dot for the front carbon, a circle for the back carbon, to make it really clear what's attached to the front carbon is going to come off the dot. What's attached to the back carbon is going to come off the circle. So that's how our Newman projections are going to work, is it's going to help us look down this bond, and it's going to show us any sort of overlap as we rotate this bond, because we're going to, again, have free rotation about this bond. So this bond can spin, but we're going to have certain amounts of energy associated with whichever conformation we take, whichever location it stops in, it's going to have a set amount of energy associated with it. So that's what we're looking at, is our staggered is where the in plane are on opposite sides. And so we're going to get this Newman projection where it looks like the spokes on a wheel, where you get all 6 fanned out, where there's 60 degrees between each 2. So between the red and the blue is 60 degrees. Between the blue and the purple down here is 60 degrees. Between the purple and the white is 60 degrees, and so on. For eclipsed, what we're looking at is now our in plane are on the same side. Could be both top, both bottom, whatever, but they are in plane. They're putting to the same side of that carbon. You're making this U shape with our in plane bonds, with the lines. So now my two are pointing out at me. These are pointing away from me. When I look at this Newman projection, when I take this perspective where I look on the side and I turn this at you, now they are directly, there we go. They are directly overlapping with each other. So you can't actually really see what is behind each one. So what we're going to do is we're going to slightly offset it in our eclipsed form. There's the camera. We're going to slightly offset it to help emphasize that it's there, but there's a clear big gap between them, so that there's going to be 0 degrees between these two, the eclipsed bonds, and 120 between each of the additional attachments. When we're looking at it drawn flat, is what I'm saying. Not like an actual bond angle, just in the picture, how it looks, right? So you can offset it slightly to the left or the right, whichever way. We're just going to do like a slight whoop, just so that we're showing that they're right next to each other. So we have the difference of this is staggered, this is eclipsed, staggered, eclipsed, staggered, eclipsed, right? So let's go back to the notes. Okay, so that's exactly what we are representing here, is we had those in line, the wedges and dashes, that was that same molecule. And then what I'm doing is I'm taking the perspective of, here's my eyeball looking down. Here's my eyeball looking down that bond. I like to represent the eyeball as this. So these are my really long lashes. There's my little eyeball. Sometimes I like to make myself a whole little person so that I know my top and bottom. I'm all eye. I don't have a head. I'm just one big eye and little stick figure. But that's trying to represent my front carbon and my back carbon. So that my front carbon is this dot, my back carbon is the circle. So I have these 3 bonds coming off the front, and then the 3 bonds coming off the back circle. Staggered is my lower in energy. Eclipsed is higher in energy because now our bonds are closer together and our atoms are closer together. So we get that U shape going on. And when we're looking down that bond, now we have them directly on top of each other in the Newman projection. That's how the Newman projections are really helpful. When you're trying to define the perspective, saying that what you're looking, which bond you're looking down, because there are going to be multiple bonds that we can look down, you're going to define it as whatever's in the front and then the back. So this would be, if that's carbon 1 and carbon 2, then I am looking down the C1, C2 bond, where C1 is the front, C2 is the back. I could look down the C2, C1 bond. It would just be as if I'd flip this around so that now it would look like this. As if I took this and I flipped it over like a pancake. That's what I'm doing, is I'm looking down the other direction. So you can take either perspective, but when you're listing out the bond you're looking down, the front carbon is listed first, the back carbon is listed second. When we rotate between our staggered and our eclipsed, we're going to have a 60-degree rotation, and it's going to be 2.9 kcals per mole for hydrogens to overlap. So we'll talk about the energy numbers in a couple of minutes. But that's going to be what we have for hydrogen. Everything's going to be relative energies. So we're actually going to say the energy of this ethane in staggered is going to be 0. Everything's actually going to be based on ethane, is going to be our 0 point. So with our Newman projections, the easiest way to know which of the staggered conformations you need is to look at where the front carbon and the back carbon line in plane lines are located. Are they pointing up relative to the ring, or are they pointing down relative to the ring? Remember that the dot is our front carbon, the circle is our back carbon. When we are converting from bond line to Newman, we need to pay attention to that relative perspective. So again, that front carbon is listed first. If the molecule isn't numbered for you, assume IUPAC numbering. That's our nomenclature numbering. So that is what is the actual location according to the name. That's what you would use if no numbers are given. If numbers are given, use the numbers. So if I'm told to look down the C2-C3 bond of pentane, pent is going to be 5 carbons, like a pentagon has 5 sides. A pentane has 5 carbons, ane being all single bonds because it's an alkane. So I'm going to just draw my zigzag pentane. I'm going to number these left to right because structure wasn't given to me, so I can pick however I want the perspective to look. So I'm just assuming I'm looking down this way. So when I'm looking down the C2-C3 bond, that means that I am looking here. Carbon 2 is in the front, carbon 3 is in the back. Here's my little eyeball looking down. C2 is in the front, C3 is in the back. So to actually draw my Newman projection, start by drawing a circle and a dot. Get with the basic of our Newman projections. So we get the dot, we get our circle. Then we need to look at that front carbon and see if that in-plane line is going straight up or straight down. So when I look at this relative to here, so if this is my little body, right, and I am in line with that C2-C3 bond, I see that the bond off of carbon 2, that in plane, the line is going down, is closer to my feet. So that means I need to have a line going straight down off that dot. Off of carbon 3, the circle, I see that the line is above my head in that relative perspective. So it's going to be up. So that means off my back carbon, I need to go straight up. And then we're going to just fan out the other two so that they are 120 degrees. So I get this Y shape for the front carbon and this upside down Y for the back. That gets my Newman projection for the core. Start with the core and just make sure that your in-plane lines match up, that they're going straight up or straight down as you need them to. So that is now step 3, was fill in the rest of the bonds. Get it to be either a Y or an upside down Y. Now we're going to fill in our substituents. It's important to note that for the Newman projection, we're still assuming our line diagram structure. So that means that because I have to have a line, I can't omit the line in a Newman projection. The lines must be there. You must have the 6 lines. I must also show a hydrogen because my line diagram tells me that these are all carbons, that they're all CH3s. So I'm balancing these 2 rules. So in my Newman projection, if I want this N to be a hydrogen, you got to write in an H. You got to be explicit with these hydrogens in the Newman projections. So when I look at this, carbon 1 is that methyl, so that's fine. I don't have to draw anything there, just is a straight line. That's it. It's a CH3. The other 2 atoms coming off of that front carbon pointing up are the hydrogens. So I have to have a hydrogen going up and to the left and up to the right. Those are the hydrogens on carbon 2. Then on carbon 3, I have my 2 hydrogens that are going down, and then I have this ethyl, this 2-carbon chain. So I could either show it as just a line showing that there are 2 carbons, in which case then this would be numbered 1, 2, 3 is the circle, 4 is that bend, 5 is the end. Or I could represent this part. I could abbreviate it in a condensed form to write CH2, CH3. Or I could write ET, write my abbreviation for an ethyl chain, for a 2-carbon chain. So just like that for carbon 1, I can also write just a CH3, or I can write ME, which is my abbreviation for methyl, for a 1-carbon chain. And again, that's in the nomenclature video where it talks about that. And now we're done. So that is our Newman projection for this exact conformer of pentane looking down the C2-C3 bond. All right, so let's say I want to do the same structure, but now I'm looking down the C3-C2 bond. So I'm going to duplicate this. But now C3 is my front, C2 is my back. So now C3 is my front, C2 is my back. So now 3 is my dot, 2 is my circle. So I'm going to be looking this way. Put the pupil outside my eye. There's my little pupil. Here's my little body going down on the page. So this is that perspective. So again, I do the same steps. So I put a circle and a dot. Now I look to see where are the in-plane lines. Where's the straight up and straight down? Straight up is on carbon 3 on my front carbon. Straight down is carbon 2 on the back carbon. And then I fill in the upside down Y and the straight up Y. Note that the Y's are only in the stagger conformation when you get the upside down. And so like this is the normal Y, there's the upside down Y. You only get that in staggered. In your eclipsed, they would both be upside down or they both would be right side up. These are still just examples of staggered at the moment. We'll do one after this that's our eclipsed to see what that looks like. We'll do the conformation of this. So our ethyl is now on that front going up, and then my other 2 bonds are hydrogens. The methyl is what is going down on the back, and then the other 2 are hydrogens. So this is the Newman projection of that same molecule, just looking down the other perspective, looking down the backside of the C3-C2 bond instead of the C2-C3 bond. If I had rotated this conformation so that I drew it like this, and I say, look down my C2-C3 bond, then I'm going to do my circle, my dot, and I again look for where are the straight lines. Off of 2, it's straight down, straight down. Off of 3, it's straight down. So I draw it straight down. So now I'm going to finish it out to make my Y for the front. And then I have this Y coming off the back, and it's just offset a little bit so that I know that they are essentially, they're truly on top of each other, but I just can't draw that. So I draw them just offset a little. So now my methyl is what's coming down in the front. My ethyl is what's going down in the back. And then my hydrogens are on top of each other there. You will be expected to assign wedges and dashes to know if it's going to be the left or the right side. So if I imagine a, whoops, wedge and a dash, I have to imagine where this is on my body. So if this is that eclipsed conformation again, let me stop the sharing and let me make this big again. Oh, wait, can I? I hope this worked in the recording. I tried to make myself big, so I hope I'm big now. If not, build a model kit and do this yourself. Okay, so when we're looking at this, if this is my eclipsed conformation, these are the wedges, the white and the red pointing at you. So big red, little white pointing at you. Those would be wedges. Then the little green, little purple in the back, those are the dashes. The blue, the big blue, the little orange, these are the lines. They are in plane. So when I take this perspective, then, and actually here, let me start from being you. So these are my wedges. They're pointing at us. We all have the same view now. When I go to rotate this, these wedges are going to now be on my left when I turn that. So the wedge got moved to the left side in my body view. I could have also rotated it. Oh, let me join you over here. I could have rotated it this way so that the wedges are now on my right. When I look at this, like this is my right. Which way I turn this will determine which way the wedges go for left or right. So it all depends on what has to be in the front. So if this is my front carbon and this is carbon 2, then that means that my wedge is going to end up on my left side. So it's like I'm taking the structure and I'm turning it. It helps to have a model kit so you can physically turn it. There we go. Okay, so now hopefully the notes are big again. Hope that worked. So when we're looking at that, in this perspective, this wedge, this is on here for this perspective, this exact perspective. This is going to end up on my right. So this hydrogen is this hydrogen. This hydrogen is the hydrogen on my left. And I can do the same thing for the back ones. So that now the, let's do purple and orange. The purple wedged hydrogen on carbon 3, that's on my right-hand side. The orange hydrogen on the dash on carbon 3, that is the hydrogen on the left-hand side off of carbon 3, off the circle. A quick trick that you can use is once you've figured out the dash and the wedge, if it's a dash and 1, if the dash is on the left and 1, it's the left on the other as well. So like if it's dashed, it's always going to be on the same side. Your wedges will always be on the same side. So you can do it really quickly. And it works for, even if it's in the staggered conformation. So if we have this staggered conformation, these wedges are going to both be, for this perspective, the wedge is now the left-hand side. So those are those hydrogens there. So it still works out. You're going to be expected to be able to know that rotation. It'll get easier the more you do it. Start with an actual real model kit so you can actually turn it and make sure it makes sense. All right, let's look at some of our relative energy considerations now. How do I actually know that there's a difference with these different conformations? So the staggered conformation, the distance between your sigma bonds on the front and the back carbon is known as your dihedral angle or your torsional angle. So in our staggered conformation, we get it to be 60 degrees, 180. Oops, that's the same one. 180 and 300. There is no torsional strain. I'll define these terms on the next slide. Just be aware of the fact that there's no torsional strain in the staggered conformation. Your lowest energy conformation is the staggered conformation, but we have two possibilities in our staggered conformation. We can have it be gauche or it can be anti. So we have those interactions are possible. Anti is going to be where your largest groups are 180 degrees from each other. Gauche is when they're going to be 60 degrees from each other. The energy of two staggered hydrogens is that 0 point that I was telling you about. Everything's going to be relative to our staggered hydrogens, which is 0 kcals per mole. In the eclipsed conformation, now we have torsional strain. Torsional strain is when electrons repel each other from eclipsing bonds. This is known as Pfitzer strain. That word doesn't matter. I'm going to always use torsional strain. It's the eclipsing bonds themselves. So our torsional angle is going to be 0, 120, and 240. The energy of eclipsed bonds is about 1. That is known as the rotational barrier because it's 1 kcal per mole to get past each individual one of those eclipsed hydrogens. Your eclipsed conformation is going to be your highest in energy. It's important to note that there's going to be a difference between torsional strain and steric strain. Torsional strain is where the bonds are actually repelling each other, like the orbitals themselves are repelling each other. It was previously believed that the conformation was high in energy because of sterics, but they've discovered that it's these atoms are actually like the atoms themselves are far away from each other. So there isn't any steric interaction for ethane. It's actually repulsion of the bonds themselves. That is torsional. Repulsion of the bond, the electrons in the eclipsing bond. That is torsional strain. Sterics is going to be if the things are too big near each other. So let's illustrate these terms. So anti, we said the two largest groups are 180 degrees from each other. So yeah, it's just literally whatever is biggest. In torsional strain, it must be in the eclipsed conformation because it's the eclipsing bonds. So we get torsional strain is between the bonds that are overlapped. Our anti-conformation, sorry, I forgot to mention this. This is the most stable conformation possible, is the anti-conformation. So that's going to be the absolute most stable. We then have steric hindrance. Steric hindrance can occur in our staggered and eclipsed conformation. Sterics is essentially atoms are too close together. They're bumping into each other. They are unable to occupy the same space, so they bump and they're trying to get away from each other. That is sterics. It is high energy because they're too close. In the staggered conformation, it is called a gauche interaction. So the steric interaction is specifically a gauche interaction when you are staggered. So it's a type of steric hindrance where you have two non-hydrogens that are 60 degrees apart. So I only have a steric interaction between the methyl and the bromine here. Everything else is not a steric interaction, is not a gauche interaction because there's hydrogens. It's not two non-hydrogens. Sterics get abbreviated by these overlapping parentheses to indicate that it's just saying that they're too close together. It's just a symbol to represent sterics. So this gauche interaction here is that steric interaction because of two non-hydrogens that are too close together in the staggered conformation. Totally eclipsed is going to be where your two largest groups are now eclipsing. This is going to have the greatest amount of sterics and torsional interaction. So totally eclipsed is where we see our two largest groups are eclipsing. That's totally eclipsed. Energy tables will always be given to you. So you do not memorize these numbers. Whenever you need them, they will be given to you. So hydrogens that are overlapping, a hydrogen-hydrogen bond, is eclipsing will be 1 kcal per mole, or it's 0 if you are gouged. For hydrogen methyl, it's 1.2 if it's in the eclipsed conformation. It is 0 if it's gouged because there's no gauche interaction with a hydrogen. It's two non-hydrogens makes the gauche interaction. Then your two methyls will be 3 kcals per mole in eclipsed, or it'll be 0.9, which is essentially 1 in the gauche interaction. It's important to also note that if you are in the eclipsed conformation, you only care about the eclipsing column. If you are in the staggered conformation, then you only care about the gauche column. You do not need both columns. You would just pick whichever column is relevant to you. So you would pick this column if you see that you are eclipsed. You would pick this column if you see that you are staggered. And then you would just ignore the other one depending on whatever conformation you're in. That's how you would use these energy tables. So let's actually look at this Newman projections. So when looking at this, if I take this perspective So that I'm looking down these two bonds. How did I know I had to be looking from the left side of the molecule? Yeah, it's the fact that this line's going up, right? It's that bond in the front is going straight up. If I took this perspective, the bond in the front would be going straight down. So I couldn't be looking at it from the right-hand side because I needed a line that was going up. So I had to be looking at this from the left side of the molecule. So I'm looking at this perspective down this bond. So this is 1, 2, 3, 4, and I'm doing a C2, C3 perspective. So when I look at this, I have methyl 1 is going straight up. 2 is my dot, 3 is my circle, and 4, carbon 4 is going straight down. So because I'm in this perspective, the wedge is now on my right-hand side. So HB goes here. HA goes to the left. Then HC is also wedge. So just as I told you, if it's on the wedge, and I already know HB is on the right, wedges are on the right, that means HC is on the right, and then HD is on the left. So that's how I go from that line diagram to that Newman projection. And if I switch any of them, it is wrong. That is the only correct way to draw that Newman projection, looking down that perspective. That's it. So to calculate my energy, this is the staggered and anti conformation, because my two largest groups, methyls, I have 4 atoms there. That's always going to be bigger than 1 atom. So I have 4, I have a carbon, 3 hydrogens. It's going to be bigger than a hydrogen. So my big groups are 180 degrees from each other. So when I look at my energy table, I'm looking at, okay, I have a CH3 and an H that's there. That's a 0. And then I go, okay, cool. What is the HH? That's 0. HCH3 is 0. HCH3, 0. HH, 0. HCH3, 0. Because I don't have 2 non-hydrogens next to each other. So I could have really easily just said, this is going to be 0 kcals per mole. And I can immediately do that because of the fact that it is the anti-conformation. And I don't have 2 non-hydrogens next to each other. There are no Gauss interactions for this molecule. Some of them will have Gauss interactions. This one doesn't. So if I hold the front carbon steady and I rotate my back carbon, and I'm going to rotate it 60 degrees, and I'm arbitrarily picking clockwise. So HD now goes behind the methyl. My HC is behind HB, and my carbon 4 methyl is now behind HA. That is my eclipsed conformation. The energy associated with each of these interactions is that 1.2 kcals per mole. H over H is just 1. H over methyl is 1.2. So each of these are 1.2. H over H is just 1. So now I just add it up. 1 plus 1 plus 2 plus 1 plus 2 is 3.4. And we're going to disregard sig figs. The cool thing here is looking at this, I can know exactly how much of that energy is due to sterics. So because of the fact that the torsional strain is 1 kcal per mole, so that means that I have 0.2 kcals per mole for this steric interaction. Because here, there are no sterics, So this is telling me my torsional strain, where it's purely torsional, it is 1 kcal per mole. All right, let's rotate that back carbon another 60 degrees. Now HD is in the upper right, HC is straight down, and carbon 4 is in the upper left. Now I see a Gauss interaction. So this is gonna be staggered and Gauss. The energy from the methyl-methyl is 0.9. So that part is 0.9, and then each of these are still 0 because they're they are not two non-hydrogens. Here's the only place where I get two non-hydrogens because they're methyls, they're not hydrogen. So that's the only place where I actually have an energy. So my total energy for this is 0.9 kcals per mole because I'm just adding up each of these values. So this is staggered and Gauss. If I rotate that back carbon another 60 degrees, now I have my methyls are eclipsing. HD is now behind HB, and HC is now behind HA. Now, the methyl-methyl eclipse is 3 kcals per mole. Hydrogen over hydrogen is 1. Hydrogen over hydrogen is 1. So I have 5 kcals per mole. This is totally eclipsed. Because my two largest groups are on top of each other. So this is my totally eclipsed conformation. It will always be the absolute highest energy conformation because it has the biggest things on top of each other. It has the most sterics. If I take that back carbon, now rotate it another 60 degrees. Now I get HD pointing down. My methyl is in the upper right and HC is in the upper left. I have 1 Gauss interaction, so it is staggered and Gauss. And it is again 0.9 kcals per mole. If I take that back carbon and I rotate another 60 degrees, now HD is behind HA, HC is now behind my methyl, and my methyl is now behind HB. That is going to be a total of 3.4 kcals per mole. If I take that back carbon and I rotate it another 60 degrees, I get back where I started. So these are all of the possible Newman projections from that same perspective. You always keep the same perspective when you're doing this rotational energy barrier diagram, when you're trying to consider every perspective. So to actually do that barrier to rotation plot or that rotational energy barrier diagram. Yeah, I said that right. It is now going to be graphing this. So we're going to assume this is our 0 point. It's not always going to be your 0 point. Anti isn't always staggered, or 0 degrees isn't always the staggered anti-conformation. It could be eclipsed. It's all going to be just relative. I'm defining it to this time, say that this is 0, because this is where we started drawing, and then we went 60 degrees out from there. So that this is 0, 60, 120, and so on and so forth. So my 0 point was staggered and anti. So I have at 0 degrees, it was 0 kcals per mole. At 60 degrees, I have the 3.4 kcals per mole. So this was staggered and anti. And then I get my eclipsed is right there. And then I drop down to 0.9, where I am staggered and Gauss, or Gauss. Then I go up to 5 at my totally eclipsed. Then I drop down to staggered and Gauss. Then I go back up to eclipsed at 3.4. And then I drop back down to staggered and anti, back at the place where I began at 360. So when I connect these dots, that is my rotational energy diagram, or my barrier to rotation plot, where it is that dihedral angle that, how much did I rotate the back carbon is on the x-axis, and then the relative energy is on the y that you calculated by looking at that energy table. And then you just graph it. So this is this. You just drew this plot. So you want to be able to interpret these and know what they look like. So you can draw them yourself, but you can also look at their relative perspectives. All of these are starting staggered, but I could have started eclipsed. Like I could have started here, and then this is just over there, so that it would just become, wherever you read, you can have a different 0 point. It all just depends on what your initial perspective is. I hope that makes sense. All right. That is everything to do with our Newman projections. Again, make sure you check out the other videos for the nomenclature and the functional groups. All right, I will see you next week. Bye.